All right, hi everyone. So we are now moving on to chapter 3, and this is going to be all about number theory and the real number system. So our first topic is going to be about prime and composite numbers. So for this lesson, we will be determining divisibility, write the prime factorization of a composite numbers. We gotta find the GCD, greatest common divisor, and also the greatest common divisor of a number, um, the least common multiple of two numbers, and also how we can solve problems using the least common multiple. So when we talk about number theory, we are primarily concerned with the properties of numbers used for counting. So the numbers that we use for counting are the set of our natural numbers. Now, natural numbers that multiply together are what we call as the factors. And when you multiply them, the result is what we call as the product. So in these examples, you can see 2 and 12 are factors of 24. Now, aside from 2 and 12, you can also have 3 and 8. When you multiply them, it's also 24. The same with 6 and 4. Okay? Now, when we talk about divisibility, so in the simplest way to explain this, when you divide a natural number A and B, A is divisible by B if after dividing, it has a remainder of 0. Okay? So it means it divides the number evenly. So in this case, you can have the symbol. So this one, so you have the letter B, and then that vertical line, and then A. This is read as A is divisible by B. Okay? If it's not divisible by B, so A is not divisible by B. Okay. Now we have some divisibility rules. We'll go over the most common ones. So when you are working on any number, the easiest divisibility rule will be to look at the end digit, the last digits. And you have to check it by the divisibility of 2, 5, and 0. So how do you check divisibility? Any even number, it means it ends with a 2, 4, 6, 8, 0, is divisible by 2, can be divided by 2 evenly. Any number that ends with a 5 or a 0 could be divided by 5. And then any number that is divisible by 10, okay, anything that ends with a 0 could be divisible by 10, okay? The next easy ones, still on the last digits. Now this part, a little bit tricky because you have to look for the last two digits, okay? If you take a look at the last two digits of a number, then if you can divide it, or if it is a multiple of 4, then that whole number is divisible by 4. When it comes to 8, it's pretty much the same rule, but you have to look at the last three digits. So if you can divide the last three digits of a number by 8, then that is divisible by 8. Okay? So these are the divisibilities when you are looking at the last digits of the numbers. Now, there's also another way of finding the divisibility if you are adding or getting the sum of the digits. So for example, when you are checking for divisibility of 3, all you need to do is add all the digits and make sure that it is a multiple of 3. Okay? I'll give some examples in a few. 9 is the same thing. So if you add the digits and it is a multiple of 9, so what are the multiples of 9? 9, 18, 27. So if the sum of the digits is that, then you have something that is divisible by 9. Divisible by 6 is special because it needs to be both divisible by 2, meaning it has to be an even number, and if you add the digits, it has to be a multiple of 3. Okay? So let's have some examples on divisibility. So let's check for the divisibility of 36. Okay? All right. So when you are checking with the divisibility, you start with the easiest check, which is the last digit. So we check for 2, 5, and 10. Okay? Does it end with an even number? Yes. So this is divisible by 2. Does it end with a 5 or 0? No. So it's not divisible by 5. Definitely not divisible by 10. So it's not like that. Okay? Now let's take a look for the divisibility of 4 and 8, meaning the last two digits. Well, as you can see, we only have two digits for the number 36, and 36 is a multiple of 4. So this is divisible by 4, okay? With the rule for 8, you need to take a look at the last three digits. Unfortunately, we do not have a third digit here. So, and 36, you cannot divide it by 8. So, divisibility by 8 is not a go. Next, we get on the sum of the digits. So, we have 3, 9, and 6, okay? So, let's add the digits. 3 plus 6 is equal to 9, okay? So, is 9 a multiple of 3? Definitely. 9 could be divided by 3. So, this is divisible by 3, okay? Oops, sorry, my bad. That's a good one. Well, as we see here, we added the digits. 9, is it a multiple of 9? Yes. So, this is also divisible by 9. Now, the easiest way, you don't have to check too much on 6. All you need to do to check on 6 is 2 in there and 3 is there? When both of them are divisible by 2 and 3, automatically, this is divisible by 6. So 36 can evenly be divided without any remainders by 2, 4, 3, 9, and 6. Okay? Let's have a larger number. Let's say we have the number 120. Okay. So again, let's check for divisibility. Let's start with 2, 5, and 10. So 2, 5, and 10. Let's see. Even number? Yes. So this is divisible by 2. Does it end with 5 and 0? Yes. So this is also divisible by 5. Does it end with 0? So yes, it's also divisible by 10. All right. Good. Now, let's check for 4 and 8. Okay. 4 and 8. So if you take a look at the last two digits, that's going to be 20. 20 is a multiple of 4. Therefore, this is divisible by 4. Now, the tricky part is with 8, okay? Because you have to really do some long division here. So 120 divided by 8, if you use your calculator, you will be getting 15 evenly. And so, this is also divisible by 8. All right? Next, let's check on the sum of the digits. So, we have 3, 6, and 9. So, we add the digits 1 plus 2 plus 0. That is equal to 3. So, is it divisible by 3? 3, yes. Is it divisible by 6? Well, we have 2, we have 3, so automatically 6 is also there. Now, when it comes to 9, what is the rule for the divisibility of 9? The sum needs to be a multiple of 9. Remember, the sum should be 9, 18, 27. Unfortunately, the sum of these digits is just 3. So 9, 120 is not divisible by 9. Okay? So that's our example. So let's have prime factorization. So when we talk about prime factorization, we have to be able to distinguish what are prime numbers and composite numbers. Prime numbers are natural numbers whose products are only itself and 1, meaning you cannot divide it anymore. So for example, your prime numbers are 11, okay? 11 is a prime number. You cannot think of any two numbers that if you multiply will give you 11, okay? Two natural numbers, okay? What else? 29. 29 is another prime number. Cannot think of factors for 29. Composite numbers, on the other hand, could be expressed as factors of different numbers aside from the number and itself. So, for example, you have 12. That is a composite number. Why? You can have it as 4 times 3. You can have it as 6 times 2. You can have it as 12 times 1. So, that makes it a composite number. Right? So, when we talk about the fundamental theorem of arithmetic, it means that any composite number could be expressed as a product of prime numbers. And that process is what we call as the prime factorization. Okay? Now, I'm pretty sure you've learned in middle school or probably elementary some ways of doing prime factorization. You can use the inverted division, but I would highly suggest that you work with the factor tree. Okay, so how do we work with prime factorization? So let's take a look at 70. Okay, oh, sorry, not 70, 700. So when we do the factor tree, let's take a look at what prime factor can easily divide 700. Now, the easiest way to do this is to make sure you know your divisibility rules, okay? Now, miss, it ends with a 0. Can we divide by 10? Definitely, yeah, you can do that, okay? But I would suggest, if you can start with a prime number, then do that, okay? So there are multiple ways of having your prime factorization, but in the end, the actual product, the actual factors will be exactly the same, okay? So since we are ending with 0, we know that this could be divided by 10, okay? So 10 times 70, all right? Is 10 a prime number, or can you still divide 10? Yes, definitely. 10 could be divided as 2 times 5. Can you still further divide 2? No more. So once you have a prime number, circle it. Can you still divide 5? No more. So again, this is a prime number. Okay? Now let's take a look at the other one. We have 70. Can we still divide 70? Definitely, because it ends with 0. So we can divide it by 7 and then 10. Can we further divide 7? No more factors for 7, so this is already a prime number. 10, on the other hand, as we can see, is still divisible. Could be divided by 2, which is a prime, and 5, which is a prime. So the prime factorization of 700 is simply you multiply all of those circled numbers. So I would suggest you have them in order. So 2 times 2, so that's that, times 5 times 5, and then you have times 7. Or sometimes MathLab will ask you to write it in exponential form. So you can have it as 2 to the second power times 5 to the second power times 7. Okay? So that is how we can work with the prime factorization of 700. Let me give you another example. So let's say we have 150. Okay? So again, easy divisibility. It's ending with 0. So we know it's going to be 15 times 10. Can we divide 15 still? Yes. This could be divided to 3 and to 5. And 3 and 5 are both prime numbers already. 10, on the other hand, could be simplified to become 2 and 5, which is also prime. So in this case, 150 is simply the product of 2 times 3 times 5. How many 5s do you see? 1, 2. So 5 squared. All right. Last example before we move on to the next one. So let's have the number 720. Okay. So as you can see, you can always easily divide my examples with 10 since they are all ending with 0. So let's have, this is 10, this is 72. 10 could be replaced by 5 and 2, and they are both prime numbers. 72, if you have it quickly, that's an 8 times 9, okay? 8 could be divided by 4 and 2, and then 4 could be branched out to 2 and 2. So these are already prime numbers. On the other hand, we have a 9, this is a 3, and a 3 also here. So 720 is going to be 2. How many 2's do we see? 1, 2, 3, 4. 2 to the 4th power times 3. How many 3's? 1, 2. So 3 to the 2nd power times, we only see 1, 5. And so that is the prime factorization of 720. Okay?